Hi everybody, so look, this is bite-sized chemistry for chemical bonding and VSEPR shapes, part 2. Okay, so we're going to look at 2017 and probably 2016 or something along those lines. So starting off 2017, we can see here we're left with a definition, and again, like I've told you before in the last video, electronegativity comes up all the time. So you really do need to know that one inside out. It's the heart of this chapter, so there's really no avoiding it. Now, next part is to draw dot and cross diagrams to show the bonding in a molecule of, and you're given the following there. Okay, so let's have a go with NF3. Again, if we're looking at NF3, I'll just do part I there actually, just to break it up. I. If we're looking at NF3 there, okay, N is on its own, so N obviously being nitrogen. Okay, so nitrogen is in the center. Okay, so nitrogen goes here. Now, ask yourself this. How many electrons does nitrogen have in its outermost orbit? What group is it in? Okay, it's in group 5. So therefore, it should have 5 electrons in its outermost orbit. Okay, that's grand. And if we're looking at it, we have 3 fluorines there. So 3 of those 5 electrons from nitrogen are going to bond with fluorine. That makes sense. And if we're doing the maths there correctly, and it's not difficult, 5 take away 3 is 2. So that means we have 2 electrons left in nitrogen that are not bonded, which means that it can be a lone pair. So all you do is you stick your lone pair on top over here, because there's only one, and we always put it there, like so. And now we're going to put in the rest of the bonds. And I always remember that for this, you're going to be the bonds are going to be at an angle closer to one another, simply because fluorine goes here, fluorine goes there, fluorine goes there. Why is that the case, Ryan? Because a lone pair, okay? Because it's so electron dense, it's pushing the fluorine, which would normally be at 120 degrees, closer to one another. So that's the case. Okay, and again, draw in all the electrons in fluorine. So we have 1 here, 2, 3, 6, 7. And again, I just did dots there. You can make this bigger if you want. You really should probably make it bigger so that the examiner can see it properly. Okay, so no harm there to make it bigger. Okay, next. All you have to do was just draw the dot and cross diagrams. You didn't actually need to name these or anything like that. It was BF3. So B is for boron, okay, and obviously it's the center one there. So we put boron here in the center. Grand. Okay, go to the periodic table and find out what group boron is in. Boron is in group 3. So that means it has 3 electrons in its outermost orbit. And if we're looking at it, it's BF3, so that means it's going to have 3 bonds as well. So I'm just going to do 3 electrons as far apart from each other as possible. And we put in our fluorines here. And fluorine there. And you put in your X's. 1, 2, 3, 4, 5, 6, 7. Okay, and we can see there that's going to have an angle of 120, because 360 divided by 3 is going to get you 120. Okay, our last part now is ClF. So that's chlorine and fluorine there. Well, there's only 2 of them, so there's really only one option that you could have for this. It's going to be like this. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so that's the only option we could get for that. So in this case here, it's going to be linear. Okay. Use electron pair repulsion theory to predict the shape of the molecule in boron trichloride. So we have to predict the shape over here. And I've already said it. Okay, it's going to be trigonal because it's a triangular shape, planar because it's flat. Trigonal, planar. Okay, and if you have to account for that shape now, guys, if you were asked to account for that shape there, you just say how many lone pairs and how many bond pairs, but you weren't asked to in this case here. So our next question is IV. Indicate on the bonding diagram chlorine monofluoride, so this is over here, any full or partial charges that you'd expect from the bond between them. So use electronegativity values there, okay? You always go to the those route, okay? So if it's polar, there should be a charge present, a partial charge present, to be precise. So chlorine is 3.5, and fluorine is 4, which is the highest. So 4 minus 3.5 equals 0.5. So it's going to be slightly polar. So how do I know which one of these here is going to have the delta negative charge and which one over here is going to have the delta positive charge, the dipole I should say. Because there will be a dipole charge on one of these. Okay, so I'm just going to do a different color for us. And we do our delta sign like this. Okay, so which one's going to be positive, which could be negative? Well, the negative one will be fluorine, and simply because it has the greater electronegativity. So the one that has the greater electronegativity is the one that has the negative charge. So that means at any one time, even though they're sharing electrons, at any one time, electrons are closer to fluorine than they are to chlorine, simply because it's more electronegative. And it's negative because the charge on electrons are negative themselves. So if it's closer to the fluorine, it has to have a negative sign here. Now this is really important. I have a delta sign there, that's how we represent this, okay, indicating our dipoles. If you do not put that dipole inside here, well then it's no longer a covalent bond, it's now an ionic bond. So to be really, really, really careful about that. Okay, so indicate, and that's what we did there on the charges, so we've done that part of it. Okay, grand. And predict the type of bonding in chlorine monofluoride. Well, we said it already, it's going to be polar, so all you have to do is write down for V is going to be polar covalent. That's it. If you want to write down slightly polar covalent, that's fine too. It doesn't really matter. As long as you have the word polar in it. And don't forget to mention covalent. I always recommend my students to be putting in the whole part of it. So they often just like to simplify things and just write down slightly polar or whatever, or largely polar, and they forget to put in the covalent part of it. So just be careful there. However, marking schemes are quite generous, and polar is generally what you need. So you can kind of see that 2017 question 11 was very similar to a previous one that we've done, 2018 and 2019. Definition, draw out some shapes here, and use your electronegativity values. Okay, let's move on. So 2017 question 4, identify in ammonia the type of intramolecular bonding, intermolecular bonding. Okay, so let's just draw out ammonia, and this is one of the few that you do need to know off by heart. Ammonia is NH3. Okay, so we draw out my nitrogen and hydrogens. It doesn't have to be perfect shape here at all. Okay, so let's do the intrast. That means the bonding within. So there's 3 options I could have here. It could either be ionic, polar covalent, or non-polar covalent. Use your electronegativity values. So nitrogen and hydrogen. Okay, so we're looking at this. Hydrogen is, what is it, 2.1? And nitrogen is 3.0. So we have a difference there of 3 minus 2.1 is 0.9. So therefore, part I of it, again you have to specify which switch. Okay, for the intramolecular bonding, I is going to be polar covalent. Now, part 2 is on about intermolecular bonding. So intermolecular bonding is bonding between molecules. So I just literally, all I'm going to do here now is going to write out another nitrogen, or draw out a nitrogen, and 3 hydrogens, so ammonia. Like so. Okay, I'm now going to put in 9 electrons here. And the bonding is going to be represented by a dotted line. And it'll be between the nitrogen and hydrogen. Now, I have to ask myself, what type of bonding for intermolecular forces do we have? Okay, we have 3 of them as well. We have van der Waals, dipole-dipole, and we have hydrogen bonding. Now, if it's polar covalent, it cannot be van der Waals. generally. Okay, generally you can get rid of van der Waals if it's polar covalent. So therefore we're left with dipole-dipole and hydrogen bonding. Now, remember for hydrogen bonding, you need hydrogen to bond with three elements. One of the three elements has to be nitrogen, oxygen, fluorine. Okay, plus your hydrogen. Okay, and in this case here, we have hydrogen bonding with one of those elements, which is nitrogen. So therefore, our answer is going to be hydrogen bonding. If there was no nitrogen present, and it was something like, I don't know, sulfur or whatever, okay, in that case then it would be dipole-dipole. So hydrogen bonding. Okay, so we have that one done now. I'm just going to quickly check the marking scheme there in case I have to add in anything else. We don't. Okay, we don't. That was it for 2017. Let's move on to 2014 now. Okay, so 2014, define electronegativity, we've done that already. You can see it here. You're given ammonia, actually we're doing ammonia again, and another compound called selene. It's a small molecule, each of which have 4 electron pairs in its valence shell in the central atom. Account for the difference in bond angle between the two molecules. So we have 107.3 for ammonia, 109.5 for selene. Now, draw them out, okay, it's no harm, even though you might know it already. So nitrogen is the central atom, so we put it there. Nitrogen is in group 5, that means there's 5 electrons. So we have 3 bonds, so therefore we're going to have a lone pair present. So we have it like that. So 1, 2, 3. Again, the angles don't have to be perfect for this, and we write in our hydrogens. Okay, and then we have the other one, which is selene, and you can see silicon there, Si, and it has 4 bonds, and silicon is in group 4, so that means it needs 4 bonds. So it has your tetrahedral shape. So we put in our dots, our hydrogens. Oh. I put them in the wrong place, that's all. Dots here, and obviously when you're doing it, guys, you're going to be way neater. The problem is it's a lot more difficult, I find, to write on a screen than on a page. Not that my writing is great on a page, anyhow. Okay, so look, we're asked for 2 things. First one is to, the main one actually I should say, is to account for the difference in the bond angles. So all you do here is you write out your lone pairs and your bond pairs. And you're going to do the exact same for the other side too. Lone pairs, bond pairs. Okay, and if we're doing this, we have over here we have 1 lone pair and 3 bond pairs. Over here we have 0 lone pairs and 4 bond pairs. I want you to still put in the 0, okay, even though it's obvious. Okay, remember, you must treat as if the person correcting your paper has very little knowledge of chemistry. So you have to spell it out for them, basically. So that's it for the difference, guys. That's all you need to do. For it, okay, in terms of the bond angles, I should say. Okay, next is asking you to use the electronegativity values to determine the NH bond in ammonia or the SiH bond in selene is more polar. Not difficult. All you want to do now for part 3 here, I think it's part 3, doesn't really matter, we'll just put it down here as part 3, is get the difference between them. Okay, so we have nitrogen here, we have hydrogen here, we have Si here, we have hydrogen here. Go to electronegativity values. So hydrogen is going to be 2.1 for both of them. That's grand. Nitrogen we did there recently, so that's like a 3. And as Si is silicon, there is 1.8. Okay, you always take the bigger number away from the smaller number. So in this case here, we're going to have a 0.9 difference. Grand. And over here, if we're doing it out correctly, and I'm actually going to do the calculator now just to be sure, I think it's 0.4, isn't it? 0.3. exactly why I need to be doing this in calculator. 0.3 difference. Okay. So therefore, this guy over here, NH3, is going to be more polar. Because you have a greater difference. The greater the difference, the more likely, the more polar it's going to be. Next. Which of two substances has hydrogen bonding between its molecules, and to justify your answer? Now we've actually already done this, so we have an idea. But for hydrogen bonding, you need 3 elements hydrogen can bond to: nitrogen, oxygen, and fluorine. And if we're looking at it, we have nitrogen here. And over here, we have no nitrogen, we have no oxygen, and we have no fluorine. So there is no hydrogen bonding over here. So for IV there now, guys, all you have to do is you have to say NH3 hydrogen bonding, and then you have to say Y, okay? And all you need to do, that's ammonia by the way, all you have to do there is say that hydrogen is bonded to nitrogen, oxygen, and fluorine. To nitrogen, in this case, to be precise. Okay, that's it, guys, for that one, for IV. And then the final one there, give the reason why a molecule with polar bonds can be non-polar. So this comes back to our exceptions to the rule. Okay, so you have to be careful for that. Okay, and if it ever comes up, all you have to do is say symmetry, if it's symmetrical. Okay, so if a molecule that is polar, okay, but technically it's non-polar in experimentation, it's because it's a symmetrical shape. So all you have to do for that one there is for IV, or sorry, for V, it is symmetrical. That's it. Okay, and you're done for that one there. Okay, it's the only exception. Okay, as soon as you see it, you should be mentioning something to do with symmetrical. Now, next one, 2014 question 4, and you're asked for how many sigma bonds and how many pi bonds are in result from sharing valence electrons between atoms in a molecule of nitrogen. Now, a molecule of nitrogen is going to be N2, okay, and it's going to have a triple bond. Okay, that's the hard part. As soon as you know how many bonds are present, you just apply the rules, and all you have to do is learn it off, to be honest, and I only recommend my students learn it off. So for a triple bond, and this is for any triple bond now, everybody, okay, it would have 1 sigma and 1 pi, or 2 pi I should say. So 1 sigma and 2 pi. And you also need to learn off, and go back all the way over here, you also need to know off the differences between sigma and pi. Okay, so there are 2 things that you could be asked. One is going to be the differences, and then the second one there is how many in a single, a double, or a triple bond. Okay, and for a triple, it is 1 sigma and 2 pi. You're just learning off now for that one. Okay, everybody, so look, we'll leave it at that. I'll be doing a few more of these videos shortly, and we'll hopefully you'll see a lot more repetition and it'll sink in a little bit easier.